So at one point I was, when I went from Helsinki to Stockholm, you know, you write papers and whatever, and then you apply for jobs. And so, and then you have to go give talks at all these places because, you know, they're not going to give you a job. But if they don't know you, they're not going to hire you. And you can't really show, you can't just look at the piece of paper and know what it's like to work with somebody. I mean, even if the work with the paper is good, hey, the person's a jerk, whatever. It's a miracle I ever got hired for anything. That 1 year, so usually you apply for jobs in like, I don't know, Christmas time, something like that. But that means that actually starting like the previous March, you need to start giving talks and traveling around so that people know you, so that in the fall when you know, and so that's fine. So we've written some papers and given talk about it. And it was an okay talk, but.
So you went around country and talked about black holes?
Yeah, well, so I was bouncing around in lots of countries, and that was, so like, I was in Netherlands, and then, I don't know, England, you kind of bounce around it. So it was like in one stretch, I can't remember, it was like, 3 months I'd been in 7 countries. Like it was every 2 weeks I was giving a talk somewhere else, and it was like, and by the end I was bored with the talk. You know, so like for them it's the first time they'd never heard it before, so it was fine. But like for me, it's like, oh Jesus, that's slide again. Let's just zip through that one and get to the more interesting one. Anyway, that's what happens. It's hard to stay interested. That's like when you hear politicians and they say the same thing every single interview. I don't know how they do that.
They like to hear themselves talk.
I don't know, man. Like, but it's a, like, I couldn't do it.
Say it why enough times people tend to believe it.
Yes, yeah. All right.
Politics.
Okay.
Who can lie with that?
So last time, take my alien protection off. So last time I was reminding you of what we did in Physics 1. So in Physics 1, we had forces, and then we had energy. And you can describe the world using either concept. And for a lot of you guys who are in dynamics right now, it's kind of fortunate because they're going to completely mesh with what we're doing. So, okay. With the exception that in this course, we will tend to phrase things in terms of potential energy, not work. But of course, you calculate them the same way, up to a minus sign. It's really the only difference. All right. So, so can somebody tell me what the connection is between a conservative force and a potential energy? I'm not talking about politics. What's the relationship between a conservative force and potential energy? Of what gives what?
Something gives the other one.
So close. Almost right. I think you kind of know it. Go do an example. Think of gravity. What's the potential energy for gravity? What's the force due to gravity? The integral of what gives what?
The integral of force gives the potential negative integral.
There you go, right? Think about gravity. If you can make it work for gravity, you can figure it out. Okay. So at this point in the semester, I like to put on the board something I like to call the rectangle of pain and suffering. Okay, so up in the corner, we have force ideas. Down below, what? I can't decide.
It's a matter of perspective.
Well, that's just because you guys are stuck right. If you do this, it's fine.
Indiana.
I'm from Indiana, leave me alone up here. On the left,
He's right into the left of it.
You know.
no, all right. So I was gonna make a joke about letters. So,
Clever.
anyways.
Clever.
So, okay, so here's the deal. From physics 1, we had force and potential energy. Now I'll skip the joke and just go straight to what I want you to remember. From energy to force, so going this way, we would say that the force is a vector, and it's minus the gradient on u. We're going to practice today taking some gradients just to make sure everybody remembers that. Okay, but from Calc 3, you should have seen gradients, and that's how they go.
Just take the partial derivative.
Once in the x direction, y direction, z direction, put in unit vectors. Yep, and then there's a minus sign. Okay? Going the opposite direction is what Billy was suggesting, and there we have delta u equals minus the integral of f dot product. I usually write dr, but Peter was writing ds today. So since you guys just had lecture doing that, I'll write ds vector. Up to a minus sign, this is exactly work that you guys were talking about today. The question is, you can think of work coming from the outside. If I give something work and then it gets stored, then I'd say that work becomes potential energy. Yes?
It's gonna be another one of those dot products where it just becomes multiplication of standards. Or is there actual-
Many times. Yeah, many times.
So the integral, it's gonna turn into.
It's going to become simple. Yeah. Well, but sometimes the angle will never matter so much, but it's more sometimes it's with or against. So you might get a minus sign from it. That you have to worry about. Usually we choose paths where it's more or less trivial to do the actual integral. It's a minus sign. And that's where you want to think about gains and losses. Okay. Now, that's what we could have done in physics 1. We'll do some examples with that. What about here? What else? This semester, we haven't been talking about forces so much. What have we been talking about? Charges and even though you're not sure, I can't think of another E word. Anyways, the electric field, right? That's really, we're writing things with the electric field. Just trying to think of it. I'm tired. So,
Wanna come lab with us later?
Yeah, we're doing beam deflection. Interesting stuff. Interesting stuff.
I thought materials lab, you can break stuff. Isn't that kind of fun?
We did some of that, but now it's.
No. This one is a beam will bend like so insignificant. You can't even tell. So you have to use a gauge to figure out how insignificant the bend really was.
Like a couple thousandths of an inch, if that.
Plus, nobody knows how to set it up right.
It's so bad.
Well, I'll see if I might have a full schedule tonight.
Oh, yeah. Small town.
All right. So what's the connection between force and electric field? What's the connection between force and electric field?
Electric field is a type of force.
Nope. The units are different, so they can't be a type of force. The force on a test charge, on the observer, is what? QO times
Yes.
electric field created by the sources. Okay, so this relationship gives me the bridge between these. This relationship gives me the bridge between these. There's going to be another thing here. Okay, How do I tell you? It's the electric potential. V. And sometimes people use, I'll use V, but sometimes people use Greek letter phi. But I don't do that.
For charge or for?
For V, they're the same. It's just, okay, so we're gonna go through this here, but basically, the connection between force and E is gonna be exactly the same between potential energy and V. It's gonna be the same arrows, and here it's gonna be the exact same arrows that way. But we'll fill these in a minute. Okay, so these are gonna give us different ways to approach problems. You can think about energy, you can think about electric potential. What are the units on electric potential? I chose V for a reason, volts, right? So this is measured in volts, this is measured in joules, this is measured in newtons, this is a newton per coulomb. So you can approach problems from different directions, and you will need to know this rectangle of pain and suffering. Because it's basically your roadmap. You read a problem, you're given one thing, asked to find something else, you're just working your way around this thing to figure out how they go from A to B. Okay. Well, that's fun.
Huh?
Is that what they called it in Groningen?
Uh,
Rectangle of pain and suffering?
yeah, but I thought you said triangle or something.
Oh, did I say triangle?
Yeah, you said that.
All right, whatever. Well, right now I only have half of it.
It's two triangles.
It's two triangles, right? Double the fun. All right. So how do we do this? Well, let's first review. Let's first review the connection between forces and potential energy, namely these two things. So, what does gradient mean? What does that mean? It's a differential operator, so some sort of derivative. And when it acts on a function, what does it give you?
The direction point to the increase, right?
Sometimes there's something connection with maximum. What were you saying?
Like it's point to the height increase of the function.
Okay. So pointing. If it's pointing somewhere, what kind of mathematical object must it be? A vector. Okay. So it's a vector. So this symbol by itself, not acting on something, we just write it formally as x hat partial with respect to x plus y hat partial with respect to y, z hat partial with respect to z. Okay? You guys okay with this? Instead of writing the whole fraction out, it's just faster if I write partial, like just 1d. Right. Okay, so let's do an example. How would this work? For example, imagine I had a function 2xy squared. Now, is this acting on this? What would that evaluate to?
2y squared x hat plus the rest of it.
What is it?
I couldn't see the equation.
Oh.
But 4xy y hat.
Remember, partial derivatives, you just pretend that you're treating one variable at a time, so you're holding the others constant. Yeah? Okay. Now, so the very first week I kind of did a review of these ideas, but I think I'll do it again. So if you have, let's say you have x, you have y, you got some function. I don't know why I would draw them kind of the same, but whatever. And, okay. Got level curves of the function there. All right. So, what does this mean? So imagine you were to walk from this point, point 1, over to another point, call it 2. Okay? So the function clearly changes. The height, the function, the height is f of x and y. Right? So the height is a function of x and y. So when you take any smooth function, when you look really close at it, it looks like a plane. Or if you get really, really close, it just looks like a little plane that goes between the points. And so it kind of linearizes, and you can say, oh, well, the total change in the height comes from a little bit from the effect of varying x, and a little bit more from the effect of varying y. So you can kind of associate the changes in height from 1 to 2 as being due to moving in the x direction a little bit and moving in the y direction a little bit separately. That's really the idea. So is that intuitively plausible? Mason, you're looking at it like, no.
I missed the first time we said, so you said z is the equivalent of changing the x and y, is that what you just said?
So as you go from 1 to 2, the height changes.
Right.
Okay. So in reality, maybe you went straight there. Okay. But again, because it's when you get if these are really close together, you can approximately say it's a plane.
Yeah.
So then you can break it up like vectors. You can say, well, it's a little bit this way and a little bit this way. Right? It's a little bit coming from x, a little bit coming from changing y. You can break it up like that, which is only true if it's a plane, but when we do calculus, we're going to take a limit. It's close enough. Okay? So then what we would say is, okay, I would say, well, in walking from point to point, I would say, well, the change in the height, it's just a baby step because I'm making everything in a limit. So the height changes a little bit. Well, it's going to be a little bit coming from x and a little bit coming from y. Why do I have partial derivatives? Well, again, when you get close enough, it's like a plane, right? And when you're moving in a plane, x and y are independent. So that means if I'm changing x, I'm not changing y. Oh, that's a partial derivative. If I'm changing y, I'm not changing x because if they're independent. Oh, that's a partial derivative. So that's why it pops out. Okay. And then I can go ahead and, all right, so is that okay? Billy? Is that intuitively clear? Okay. So then I can repackage this. I can make a vector, ds vector, which equals x hat times dx plus y hat dy. So it's just a little baby step vector, but what it really is the tangent vector along, a differential tangent vector along the path. It's the arc length differential along the path. Like you were doing today in dynamics class, same one. So I can say, oh, and then I look at this thing and I say, oh, therefore, using this thing, I can say it is ds dot the gradient on f. Just, really it's this, but then I just dress it up like a vector.
You're multiplying the gradient by.
And it's a dot product. And when you do that, you match up the x components and the y components. You don't do the cross term. Yep. That's exactly right. Okay, so far? We did this, I think, in the first week, but it's been a while. All right. All right. So, all right, so what that means is that, okay, what if you have, you have some hill, f of x and y, and you plot out the level curves. Right, these are the curves of constant height. And I'm going to project down into the xy plane. It's like take a bird's eye view, looking straight down. In the xy plane, I would have, something like this. Like that. Okay. In the xy plane, sitting underneath this. Okay. So what we'd be saying is, well, as you walk, let's say we walk along a level curve. So, Stefan, if we are on this square and we go to on the square,
Huh? I don't understand.
you're giving me a hard time for saying triangle instead of rectangle. So there's no square. That's the deal. All right. Anyway, so if I walk from point 1 to point 2, okay, along the level curve. Along the level curve. Okay, I can just this was arbitrary, so I can just use this formula, and I would say, well, I would say the change in the height of the function from 1 to 2, that's going to be ds dot the gradient of f. From 1, where this arc length points from 1 to 2. Okay, so ds would just go like this. It just goes from 1 to 2. All right, now, but both of these, what's special about these 2 points? They aren't random. The ones over here were just random points. Over here, they're not random. What's special about them?
Same level.
On the same level curve. But that means that, what about the height? It's not changing. So what does that mean about the change in f?
0.
0. If it's not changing, then df is 0. If something's constant, you say, how much is it changing? Well, it's not. So therefore, for ds along a level curve, we get that df equals 0. Okay, now we get it. Now what does that mean?
That's because there's no change in height.
Yes, because there's no change in height. Okay. Now, how can that happen? So ds, so this has to be 0. ds isn't 0. They're different. This is not 0. So for this thing to be 0, let's kind of go through. What does dot product mean? All right, so the formula is the magnitude of ds, magnitude of gradient f, whatever that means, times the cosine of the angle between them. Okay, this should be 0. This is not 0. Without no, unless you're really unlucky, probably this is not 0. The only way to make sure this works for arbitrary functions is if cosine of theta is 0. So we learn that theta equals 0 over pi. sorry, equals pi over 2 or 3 pi over 2, aka 90 or 1 or 2/7.
You're struggling today.
I am. I'm on my I've had like 3 meetings and like, it's a rough day.
Oh, that's good.
All right, is the logic clear on how that works?
Yes.
All right, so what we learned, okay, so what I'm not gonna show you, but hopefully it's intuitively clear. This thing has no, so if you were to project this gradient of f on a level curve direction, you get 0. Therefore, it must live perpendicular to that. So it's exactly in the directions where, not where the curve is constant, but it's perpendicular to where the curve is changing the most. So gradient f is in the direction where f changes the most. Now, in what space? What variables are we talking about walking in?
X and Y.
X and Y. So when I talk about gradient of f, it lives in this space, not this space. So the gradient here would live, is a vector in this space. It's not like some vector, there's no z component, right? It doesn't know about z. So it doesn't live there, it lives here. Okay? The gradient lives in the space where you have functions, where you have variables.
But we don't have a z component for the top one, even though it's like the bottom one's bird's eye view, so you're looking at x and y, but there's no z component for the top one.
I can draw, so I can draw z components in this. There are z components here. What I'm telling you is the gradient only gives you things which live in this space. So because it's going to be partials of x, partials of y, partials of z, right? But f of x, y, what happens when I take a partial with respect to z? Nothing, right? So therefore, it'll never give you something, right? Okay, so people usually understand this fine, but they don't. They sometimes get confused over where things live. Okay. All right. Yeah. Okay. Good. Great.
So then typically we won't receive, there won't be z components in most of the work we do then?
No, but I want you to understand. So we will have z components. Let's understand that. Let's imagine. Whatever. Let's imagine I write potential energy, and it could be a function of x, y, and z. Let's try to. How would I try to do this? If I write u, which is a function of x, y, and z, and I were to make a graph of it, well, before I just had x and y. Now the underneath space is x, y, and z. And now I want to think about this as a hill on top of these. I need a fourth dimension. And I can't draw it, right? You really can't. And so that's why people actually just learn to think in terms of the level curves, because that you can draw. I can define like level surfaces. You know, okay, here's a level surface, and here's another level surface, like a sphere or something. And then you kind of have to intuit. If you're going to do that kind of higher graph like we had before, I would need x, y, z underneath, and I need some fourth dimension to put the height in. But we can't picture that, so. Okay. So we will definitely have x, y, z, but our X, Y, Z are always in kind of the base space, not the function sitting on top. Yeah. Like sometimes this gets glossed over in Calc 3. I think people, doing the calculus is really trivial, but then kind of picturing like where things live can be kind of tricky. All right. So that's gradients. Awesome. Let's work backwards. Let's do the other way. So let's apply these ideas to Coulomb's law. So let's apply it to Coulomb's law. So for Coulomb's law, that's the force of the source on a test charge observer, point charge. It only works for point charges. What is the formula for that?
K QS QO over R squared R hat.
Yeah? That's that. All right. So with potential energy, we take gradients to get to the forces. To get from here to the potential energy, what do we want to do? We want to integrate. Okay, so let's choose a specific example. Let's imagine I put my charge at the origin. So this will be the source. Okay, if I put the source charge at the origin, then this stuff just becomes radial, like spherical radial vectors. Like you can just use. So then I can just use normal kind of polar or spherical coordinates. So my RO is going to be here, and it's going to be R, just the radial vector out to it. Okay, so I drew it like it's on the, this is Z, X, and Y. I drew it like it's on the Y-axis, but really it can be anywhere. And because I put the source charge at the origin, it just becomes a radial vector. Easy. All right. Now, what I would want to do then is find, let's see. So the relationship is the change in potential energy is minus the integral of F dot ds between 2 points. So, all right, what I'm going to do is say, let's make this some point RA, and this would be some other point RB. All right. I'm going to choose them to be along the same radial direction, ray. Because if you were to choose some other point here, you could break it up into an integral here and then an integral, two integrals, do it in 2 steps. If I made this point, but when you integrate this way, you're moving in the angle direction, which is perpendicular to the radial direction. And when you use the dot product, you're going to get 0. So this integral is going to get 0 anyway. So I'm going to, without loss of generality, just choose 2 radial points because those other sideways bits don't matter. Okay. So, in going from A to B, what is the, if I kind of draw a little segment there, what is ds vector from in this interval? How long is it as you move radially? What's the magnitude of the arc length as you move radially? dr. And which way does it point as you move radially? R hat. Yeah. And similarly, because I put the electric field at the, or the source at the origin, this just becomes K, QS, QO, R hat over R squared. Right, because it's just at the origin, so it's just, everything's just the usual spherical coordinate R. Okay? So then I can use my formula, or actually Billy's formula, the one he told me, so if it comes out wrong, it's his fault. The change in U in going from A to B, so that's going to be U of, this is final minus initial, U of RB minus U of RA, using his formula up here, is minus the integral of f dot ds. So that's K Q S Q O over R times R hat dotted with dr R hat.
Your R in the denominator be squared.
Thank you. Yes. Yep. And what if the limits of integration should be from A to B. Okay, now what do? What's the ugliest thing about that formula right now? The integral? Really? Or the vectors?
R hat, right?
Hmm?
Is it R hat?
All of it? Is that
No,
right?
I mean R hat.
R hat with R hat is one, and
Because it's just gonna be like
Yeah.
vector R over the.
What happens when I take these dot products? R hat dot R hat. What does it give me?
Oh shit.
1, because it's a unit vector. So R dot R is 1.
Yeah.
And then,
Yeah.
so the angle's 0 degrees. So there's no cosine to worry about, nothing. It's easy. That's the nice thing with this path. Now it's something you can give to a mathematician. They would know how to interpret these symbols. What would they tell me? Oh, I forgot my minus sign. When I do this integral, what do I get? Integral of 1 over r squared. It's a power law. So when you integrate a power law, you add 1 to the exponent and divide by the new exponent. So if I add, so right now the exponent is -2. If I add 1, it becomes -1. I should divide by -1. So the minus sign goes away. Minus sign goes away. This becomes a 1 over r. And it's RB minus K Q S Q O R O. Phew.
R hat.
R A. Thank you. Yeah. All right. Okay. Well, what can we say about this thing? Well, let's imagine they were both positives. Both positives. If both charges were positives. So the numerator is positive. If RB is larger than RA, what can we say about potential energy?
Positive potential energy.
Hmm?
They don't have positive potential energy.
Well, I guess the change in potential energy. What is this thing, positive or negative? If the numerators are both positive, and we make RB larger than RA, what happens?
It'll be a positive.
Negative.
It's negative, right? Because this number is bigger, which means this fraction is smaller. Right? So the difference is going to be negative. Which way is the force act? If both charges are positive, I'm standing right here. Which way is the force pointing?
Out.
Out. The force always points to lower the potential energy. So a force always goes towards the direction of lowering the potential energy. So in this case, because they repel, when I move away, I'm going with the force. I must be lowering potential energy. If I go against the force, I'm increasing the potential energy. That makes sense. Think of this like a spring or something. If I go against the force, it's like compressing the spring, I've gained potential energy. Minus signs are going to be the trickiest thing. So if you can kind of think about it a little bit, then that'll help. Forces go towards lower potential energy. And if one is positive, one is negative, well, all the minus signs are flipped. So then moving away, well, then if it's positive and negative, then they're attracting. The forces pull them together, which means moving away is increasing potential energy. So it flips. Okay? All right. Awesome. Now, what is it really tempting to do? U of RB minus U of RA equals this of RB minus this of RA. It's really tempting to say then that the potential energy of, I don't know, pick one, RB equals what? What's it tempting to do?
U minus RA.
Hmm?
Total potential minus RA.
Well, I'm just saying this is a function of RB minus a function of RB equals a function of RB, RA, equals a function of RB minus a function of RA. Isn't it tempting to kind of say that it's just this? No? I think it's tempting to say that. And it's okay, but you have to understand you're assuming something. So basically, this could be wrong plus a constant, or you could shift it by a constant. And if you did that, it would always subtract. You always have that ability to shift potential energy by a constant. And it's got to be, in a problem, it's got to be the same constant everywhere. Like last semester we had gravity. We usually said potential energy was 0 on the floor. Wow, that's just a choice. You could shift it by a constant everywhere. Physically, the only thing that's important or is meaningful is the difference in energies, and then those constants subtract out. Okay, so here's what we will do. When we have point charges, we will just take this to be 0 at infinity. Say the potential energy is 0 of a point charge is 0 at infinity. So when you plug in that the position is infinity, we want to get 0. So you put in infinity, this fraction goes away. That means we will choose this to be 0. That's a choice, but it's the easy one. When we have other shapes like a line or a plane that's infinite, something like that, we will choose something else. We won't choose it to be 0 at infinity. Like if we're talking about parallel plate capacitors, we usually choose it to be 0, usually like on the negative end of the capacitor.
But if you choose your constant to be 0 at all, you're not really changing it by a constant. You're not doing anything. 0, you would choose 0. So how are you allowed to do that?
So because you never measure potential energy, you always measure differences in potential energy. So it's just never, there's no experiment that can tell you what the right answer is. Turn it around, physically, this constant, whatever it is not physical. Since there's no measurement that can make it, you can determine it. So we turn it around, we just usually go and say, oh, well, by choosing some point where we just declare that it's 0, what we're really doing is saying we calibrate all experiments relative to that point. So when we talk about point charges, we're always talking about the energy relative to a charge at infinity, which is 0. We declare that to be 0. It's really that. All measurements of energy are relative to something. This process of choosing the place where it is 0, you guys know what it's called? You've talked about it, I know.
That's the ground.
That's ground. Yeah. That's ground. So when we say that something is grounded, what we really mean is we're going to measure, we're going to make that the reference point. We're going to measure everything else relative to it. And, physically, you can probably anchor it to the ground, but that's what we're just saying. But that choosing that choice is equivalent. Okay? And that kind of clues in. We're going to choose in other shapes, not points. We'll choose ground differently at our convenience. How are we doing? Feel like what I want you to do, so I have potential energy. I want you to follow this octagon of pain and suffering and figure out the the force. If U of R is K Q S Q O over R, use the gradient to evaluate the force. Using that.
Oh, we only have one variable?
Yep, so it's easy. Okay?
Yeah.
So the formula says I take minus the gradient. So I'm going to have minus, I'm going to have R hat times partial R on U of R. Yeah? I take the partial with respect to R, what do I get? Well, I get K Q S Q O over R squared, and I get an extra minus sign. Dun, dun, dun. Coulomb's law. Notice, if you had a constant, when you take the derivative, it would have been killed. So that constant is not measurable. He's texting me. Okay. All right. We understand the connection between force and potential energy. Yeah. All right. Let's pause. Let's take a 5-minute break, and then we're going to shift to electric potential and how it's defined. But really, it's the same. If you can do this and you can do this, it's really just the same. It's exactly the same.
Pause the recording.
All right. So after that break, so really, we're going to do the same thing here. Okay. So we're going to, I'll fill in the rectangle, and then we're going to talk about it and try to get intuition about what's happening. But since we've got it, let's just do it. Basically, And going from force to electric field, we're really just multiplying and dividing by a constant, right? Just a charge. Well, the derivative doesn't care when I multiply by a constant. It just goes right through. And the integrals, constants just factor right through. So in fact, this thing potential, electric potential, can be defined, you just copy paste. So you're just going to get an arrow going this way, which says now that the electric field is minus the gradient of V, or going backwards, we're going to get change in V equals minus the integral of E dot ds. And so that's those are the connections there. And then going this way, the connection is that the potential energy of the observer is the charge of the observer times the electric potential created by the sources. Okay. So we're going to go through this and unwind it, but that's the punchline. Right? This rectangle is kind of your roadmap. You're going from one thing to the other, to the other, to the other, whatever. So I'll leave it there. I'm probably going to write that on the board every class just to remind you, because you really need to know these things. So how do we think of this? Okay, so how do we think about this? So let's kind of go back and remind ourselves how we found electric field from forces. And what we did was we imagined a whole bunch of little point charges that were source charges, and I imagined adding one more test charge as my observer, and I added up all the little forces acting on it. And then we found that there was a common factor of the observer's charge, and we factored it out, and I just said everything left behind, we're going to call the electric field. That's what I'm going to do now, only for energy. So the idea is I'm going to have a test charge here, which I'll call QO, because it's the one that it's going to feel a force, or the one we're going to say has a potential energy. And then I'm going to have a bunch of source charges here. Okay. Now, we already worked out twice the forwards and backwards, the connection between force, the Coulomb's law of force, and the electric potential energy, the potential energy. So we're just going to use that formula, and it inherits the superposition principle that we had for vectors, only now we're talking about scalar quantities. So what I would say is, if I were to write down the potential energy of this thing, I would have to say the potential energy of this charge. Well, and I'm saying I've already got these, and then I've just got one more. I want to know how much energy, the potential energy does it have relative to those. I say, well, okay, I have all these source charges. I would say, well, it's going to be K times the charge of the observer times the charge of source charge 1 over RSO magnitude. Notice it's to the first power because that's what we had up there. There's the potential energy comes with the first power, the force had a second power. So we just get first power. Also, the potential energy is a scalar, so there's no unit vector. There's no unit vector here. Energy formulas are easier because you don't have to do all this trig. It's just a number. There's no vector components. You don't have to worry about that. Okay, that's from source charge 1, and then I'd have the potential energy coming from charge 2.
Is the RSO squared?
No, that's right. The force had squared, the energy is first power. So it's just first power. So you can keep going. You could just add dot, dot, dot. So in general, we'd say this. When I have a bunch of point charges, the potential energy, the observer is K, is sum of K, Q, O, Q, S, I, summing over I, all the observers, or all the sources. The first power. Is that okay? So I'm just adding them up. Now, this is very similar to what we had for electric fields. What do we do in that case? Pulled something out. What do we pull out? Okay. K, you can pull that out with anything else that's the same in every one of these terms? Oh, that's the thing. So we're going to write this as times K like that.
Why did you put that in parentheses like that?
To really highlight the way I'm splitting it.
Well, why not pull the K all the way up?
For the same reason we did with the electric field. I'm really mimicking the same pattern. So I made that choice before. I don't want to, I'm going to make this consistent with that. You could do that, but then you're going to end up with, the formulas we have are going to have a certain symmetry between force and electric field or potential energy and electric potential. If you make the choices differently, then it's like more you got to juggle in your mind. So just don't. This thing is called the electric potential the symbol we're going to use is V. Okay. And it's what kind of charges go into it. What kind of charges go into it? Or what kind of charges don't go into it? Yeah, so therefore it must be built out of just the sources. So I'm going to go ahead and label it with an S to show that it came from the sources. Okay. So kind of lining it up, we learn that U is Q O times VS, which mirrors our formula. The force on the observer is the charge on the observer times the electric field of the sources. So that's, you see the pattern. So basically, if I shuffled the K around, then it wouldn't look so symmetric, or wouldn't look, yeah, you'd have to deal with that. All right. Okay, so what the hell does that mean? What does V measure? It measures the energy per unit charge something has. So the electric potential measures the energy per unit charge a test charge would have.
It's like joule per Coulomb, right?
Yeah, I'm going to say those exact words. Yep. Okay. So a V of S equals, I can rewrite that. And I see that Vs determines the potential energy per unit charge that a test charge would have. Okay, so it's the energy per unit charge that a test charge would have. So remember, what was an electric field? So you have source charges, they create this electric field. What it tells you is the force per unit charge a test charge would have if you were to drop it in. So if you were to add one extra test charge somewhere, one little observer, then the electric field tells you what force it would have after you multiply. Well, this is going to be the same thing. So you imagine that I have these source charges. They create an electric potential. It's a scalar, but it just fills the air around it. And then if you were to add a test charge there, it would have potential energy U, given by Q times U times V. Okay, so it's like so you have these source charges and they create an electric potential around it, which kind of, it's like the preconditions to give something a potential energy if you were to add it in. That's what it's measuring. It's like the potential, that's what it tells me. All right, so what are the units? The units of V are going to be the units of U over the units of Q. So that's going to be a joule per Coulomb. That's kind of awkward, so we give it a name. A volt. A volt means a joule per Coulomb. Okay. So let's do an example. Let's do an example. Let's do the hydrogen atom. So in a hydrogen atom, we have a proton, positive charge, and we have an electron, negative charge. And I know it's way more complicated than this, but let's pretend that it goes around in a circular orbit. Okay. Now, these are point charges, so we're going to measure potential energies relative to where? What did we say before? What did I say before? Where do we say potential energy is 0 for point charges? At infinity. So what we're going to do then is say, okay, relative to when the electron would be infinitely far away, we call that ionized. Right? When you ionize an atom, you rip the electrons off. In chemistry, you don't remember that? Chemistry, you did, okay. All right, so relative to that situation, Now we'll call that zero, when it just barely escapes to infinity, we'll say that's zero energy. Well then, okay, if zero energy is when it's really far away, which way does the force act between a proton and an electron? Pulls them in. So what's going to happen to the potential energy of the electron? Is it going up or down? Which way does the force act? So if you bring it in from infinity, are you going with the energy, or with the electric field, or sorry, with the force or against the force? With the force. And force is pointing in the direction of lower energy. Forces always go to lower energy.
That makes no sense.
Forces always go to lower energy. Think about gravity. Energy is lower on the floor. Force of gravity goes to the floor. Always works the same way. Forces
It's
drop.
zero at infinity though. Wouldn't that be the lowest?
Nope.
What's lower than zero?
Negative.
Wait, so by that logic, are we saying that somewhere, wherever gravity originates, I guess, for lack of better terms, that the ground is considered negative?
So if we say that potential energy is zero on the floor, and then you drop a rock into a well, you would say it has negative potential energy when it's in the hole.
That's stupid.
It's just a choice, right? Because of where we said zero was.
Right.
So, but that's the standard choice for point charge. If you don't choose that, you have to deal with that annoying constant. So don't make that choice. So in that case, here's what we would say. With that set of conventions, it says that an atom or an electron, which is just barely escaping, just barely ionized, has zero energy. It's kind of convenient because that means that if something has positive energy, it is ionized. If something has negative energy, it's bound. It's stuck to an atom. So it's kind of convenient. That's really that's a nice way to do it. Anyway, so what we're expecting is if zero is when it's far away and the force is pulling you together, when you start the electron far away and you walk to here, you have lowered its energy from zero, so therefore it should be a negative answer. I mean, whether you like it or not, can you at least see that it's consistent?
So we'll never have a positive answer.
If it was a proton and I brought it in, then it would have gained potential energy. It's all about the minuses.
Because they want to repel.
They want to repel.
Okay.
All right. So for hydrogen, a typical length scale is 10 to the minus 10 meters. Right? And what I want you to do then is to say, okay, relative to an ionized electron, what is the potential energy of this electron at that radius away from the proton? And you can treat both of them as like their point charges. So numbers you might need, well, the electric charge, what is that? Do we know it by now?
8.99 times 10 to the.
That's K. Right, this is 1.61 times 10 to the negative 19 coulombs. This other one was a Newton meter squared per coulomb squared. Okay. So to do that, let's evaluate the potential energy of an electron at this distance relative to the proton, where we assume that we kind of measure things relative to infinity. So to do this, what's the sort? Which one feels the effect, and which one who has the potential energy in this case? The electron. So that's the observer. So we'll say QO is the observer, is the electron. And we're applying this formula, but we just have one, just the proton. So we're going to say the potential from the source is just from the proton. That's going to be K times the charge on the proton over the distance, the first power. I'm just using that formula when I just have one source charge, so it's just the sum of one thing. And let's do that. So let's find how many volts does it experience? How many? So relative to the proton, what's the voltage? How many volts will we have? Relative to infinity. Relative to infinity. That's 9 times 10 to the 9th. Charge of the proton is 1.61 times 10 to the negative 19, divided by the distance of 10 to the negative 10 meters. And then I think to myself, man, what do I wish that number was? What do I wish that number was? 1.5. So I'm going to round this one up, I'm going to round that one down. I'm going to call it 15.
Actual is 14.
Times 10 to the negative 10, yeah, just 15.
No, it'd be 1.5, right? You add, and
Yeah, 1.5, good.
then you wouldn't have a, yeah.
No, it's 15. It is 15.
50.
It is 15. Yeah. Good. Because the 9 makes the 19 a negative 10, the 10s cancel. So all the 10s cancel, and I get 10 times 1.5, 15. What was the actual answer?
14.
Okay. Close enough. All right. What about the potential energy of the electron? How do I go from electric potential to potential energy?
Multiplied by the charge.
By the charge of the electron, which is negative. What do you get?
Negative 2.33 times 10 to the negative 18.
It's a tiny number. But that's okay, it's one atom, so you wouldn't expect it to have tons of energy. However, we can kind of see if this is even close to right, because I happen to remember the answer from chemistry class. I don't know if you're a chemist, you might remember this, but if you're not, you probably won't. Does anyone remember the ground state energy of hydrogen? It's one of those things that is famous for quantum mechanics. He calculated it exactly. The energy, the ground state energy for hydrogen is negative 14.7 eV. What does that mean? Well, remember, a volt is a joule per Coulomb. So rather than measuring charges in coulombs, in atomic physics or chemistry, you usually measure it in EVs, because that's a more natural unit when you're ionizing things and making electrons jump. So that just means it's. So what we found was 15 E times V, and it's going to be minus, because it's a negative charge. So it came out better than it could have. I mean, I just said the order of magnitude was 10 to the negative 10. I mean, that's just an approximate number. So really, I guess you could say I kind of fudged it just to make it come out right. I mean, although I just did a number. All right, so that matches what we see. You can measure this by looking at things like, don't use neon signs, but use hydrogen to make it glowing, like there's signs and stuff, the spectral lines. You remember doing that in chemistry, the little lines, the little sharp bands? That's how you get this number. Yeah. Okay? So that's an example. Let's do another one. Here's one. Imagine I've got a parallel plate capacitor, hypothetically, and I hook it up to a battery. And I'll say that there are 3 volts. So what that means is that this side is 3 volts lower than the negative side is 3 volts lower than the positive, or vice versa. The positive is 3 volts higher than the negative. Doesn't matter. Right? And then I hook it up to this thing. And what I'm going to imagine is that I have a bit of dust here that carries positive 6 nanocoulombs. Okay. What's going to happen to that bit of dust? What's it going to do? Yeah, it's going to cross the capacitor. I didn't give you the electric field, so you can't use electric fields to figure out things. We're going to have to use energy to do this, and electric potential or voltage. So what I want, so it starts from rest, and I want the final velocity on the other side. Okay. So you're going to have to use.
Do we need to know the distance?
Thank you. Yes. I don't know. Say this is 10 to the minus whatever. 1. No, 5 meters. Some little bit. Oh, and I need to give you a mass. Let's say the mass equals 10 to the minus 3 grams.
That's the speck of dust.
The speck of dust. Yeah, I need to give you a mass. You can ignore gravity on this one. How do we use energy ideas to solve things? Think about the first law of thermodynamics. What do we say? Delta U equal to work and heat. Well, we don't have any work and we don't have any heat. And delta U is going to be kinetic and potential energy. So we're basically going to say the change in kinetic energy plus the change in potential energy equals the work, which we're going to say is 0. There's nothing else to it. No outside forces acting on the system. Because I'm using potential energy, I'm not doing work. If you want to use work instead of potential energy, you move it across the equal sign. We're not doing it. Okay. So that means that the change in kinetic energy equals minus the change in potential energy. Okay. So this would be 1/2 the mass times the velocity final squared minus 1/2 the mass times the velocity initial squared equals minus potential energy final. Actually, what I'm going to do is write this as the charge on the observer times delta V coming from the source. Like that. Now, in this case, what's the source and what's the observer? What feels the effect and what creates the effect?
Battery is the source, dust particles.
The dust particle feels the effect. Its motion. We're trying to find its motion, so that's going to be it. All right, are the things that I can just set to 0? The initial. Good. Usually say that one for students. It's all bad. Yeah, they're all bad. 0. What's the change in potential? 3. Careful. Does it start high or start low? Starts high. So the change in electric potential goes from top to bottom, so it's a loss of 3 volts. So delta V is negative 3 volts.
Is that because we chose to make the direction go that way, or will it?
Yeah, because I said it started on the top and finished on the bottom.
So it can go from negative.
Of course. Yeah, of course. But what will happen is, look at what happens. It's minus Q, this is positive, times this. I want it to gain kinetic energy. It's supposed to speed up. Well, if it's going to speed up, it must lose to make that happen. So if I start on the other side, it's not going to move. It's going to stay. Right. This is the positive side. This is the negative side. It's going to stay right there. It's not going to go the other way. Yeah. If you do it wrong, you're going to get impossible. You get imaginary numbers. It's just okay. Got that, and I think we have everything else we need. So I'm just going to say P final, and it's going down. It is 2 times the charge, which was 6 times 10 to the negative 9th coulombs, times 3 volts. The minus signs go away, and then divided by the mass, which I said was 10 to the minus 3 grams. What is that in kilograms?
-6.
Yep. So that's 6 times 10 to the, I get negative 9 over negative 6. That's going to be negative 3. It's 36. I'm going to take the square root. So instead, think about that as think of that as 6 times 10 to the minus 3 square rooted 3 times 6. I can make that a 4. Take the square root of 10. Square root of 10 is like, so 3 squared is 9. Square root of 10 is going to be 3.4. Times 10 to the minus 2. So I'm going to get 18, 20 to 20.4 to the minus 2. So I'm going to get 0.204. Right? Here's your second. What do you get? 189. All right. Pretty close. Okay. No,
Actually, he picked these numbers before class and just memorized.
Yeah, right. You know.
I
I
watched you reading that book in there.
That's a book on particle physics, scattering.
Are these not particles?
Has
And we got into physics class.
nothing to do with it.
Yeah.
Just trying to
Keep
keep
going
going.
on back like this.
You guys think I would do that?
You're just like, oh,
Yes.
You want me to show you how I did it?
No,
I can do it.
I don't wanna read that book.
No, that's nothing to do with it. Here we go. Here's how we approximate it. I have 2 times 6 times 3, and I have 10 to the minus 3. You see all those, right? Yeah, okay. So this is gonna be 6 times 6, so this is 36. That's nice, because I have to take the square root. The problem is that 10 to the minus 3. Right, so 6 times the square root of 10 minus 3. And I think to myself, well, on the other hand, if this was easy, if it was even, I could do it. So I think of it that way. And then I know that 3 squared is 9. That's pretty close. So I'm going to guess that 3.1 should be square root of 10. That's got actually 9.9. So I'm close. I could add a little bit, but that's close enough. So it's 3.1 is what I should do. So I can think of this as, when I take the square root, it's going to be 6 times 10 to the minus 2 times 3.1. 6 times 3.1 is 18.6. I have to deal with this 10 to the minus 2, so I shift it over 2 times.
So if I got a bunch of physicists, put them in a room, this is how they all think, is kind of a similar, just deduct math.
They all read the books before class.
Yeah, for sure. I'll show you the book I read about
It's
this.
so inadequate.
Is any of it hard?
No,
No.
it's just knowing what to pull out and what to turn.
Well, how did I do it? I didn't use the numbers I was given. I used the numbers I wish I'd been given. That's always the answer. And then the key is just to kind of fudge it so that, and if you're gonna cheat in ways that it cancels.
One goes up, one must come down.
You know, or like before I had one on this one, what did I do? I rounded the 9 up and I rounded the 1.6 down. And then sometimes, while you guys are sitting there, I kind of do the first approximation, then I go back and say, oh, well, this is a 10% error one way, 5% the other way, I figure out, oh, well, it's probably like about a 4% error overestimate. So I just subtract off 4%. You know, it is a small town, not much to do. Do this. I will tell you though, this is a learned skill. I mean, I would say I'm better at doing this stuff after teaching than I was before, just because I'm always doing these things and I'm not going to plan it all out before I get to class because it's a 3-hour class. I can't micromanage every minute, so I'm just going to figure it out as we go. Okay.
Never seen you do that math with your aluminum foil on your head.
You are right. I bet that's the answer. Let's see. We'll do a test. See if I can figure them out with protection.
Just stop.
Little text.
So what, the aliens are shooting signals in your brain?
Well, that's what we're gonna see.
They're reading the book as we go through class.
I think he has an earpiece, somebody's calling him, right?
Let's see. Can I do the physics with this on? That's the question. I don't know. I lost my train of thought, so the outlook's not good.
We got it.
Apparently, they've been beaming it into my head the whole time. Oh. I totally lost the flow with this one. Sorry, guys. All right. So we have potential energy. Do we see how to use potential energy? The electric potential and charge to get potential energy. It's very similar to what we did with electric fields. So you do Q times E to get force. Now we're going to do Q times V to get potential energy. So then you can get all sorts of, well, hold on. Okay. All right, now we can deduce, I can't. It's like shaking on top of my head. I'm thinking about this, and I'm trying to. So apparently, they are. They're beaming it down to my head. All right, now we know. I'm okay with that. You know. All right, so, okay. So we have the potential energy is Q times V. Observer, source. The first, when we have a problem with these, with the energy ideas, first thing you have to ask yourself is who's the source and who's the observer? Because you get it backwards, you're screwed. Same, like, just like forces and electric fields. All right, let's do an example, or let's deduce something. What we found for we had a positive charge, or actually we had a source charge, and we had an observer over here. And we found the formula for the potential energy observer, and we said it was K. I'm going to write it as 1 over 4 pi epsilon naught times QO QS over RSO magnitude. So we can turn that around and find the electric potential created by a single point source. What does it equal? Here's the potential energy we found before. It came from integrating the electric field and the Coulomb's law. But once we've got it, we can turn it around and deduce what kind of electric potential a point source will make around it. Okay, so from here, what is V?
QS over 4 pi epsilon naught.
Yeah, all you do is divide by Q. 4 pi epsilon naught QO S. Okay, so if you have and again, this is only true up to a constant. It's the same constant up here. So we're saying the electric potential is 0 at infinity, which means it's equivalent to saying we have grounded the point at infinity. We've grounded the point at infinity. Is that okay? You see, it's that same choice. I'm just being consistent. So what I want you to do, so this is our formula, okay? Let's put a charge at the origin. So it's at the origin. What I want you to do is to, so it's in 3D, but we're going to make a 2D slice. Okay? What I want you to do then is to plot level curves for the potential. Just to talk about phrasing. We have potential energy, and we have the electric potential. They're connected, but not equal. If I don't say the word energy, I mean V. If I don't say energy, I mean V. The only time, if I mean U, I say energy. Otherwise, So if I just say the potential, it means V. If I say electric potential, I mean V. The only time I mean U is if I say energy. Okay, so just so we don't get confused on that, right? So what I want is for you to graph level curves for this function. It's just a scalar. You can graph level curves in the XY plane. What would they look like? We're putting the charge at the origin. So in this case, what's the formula for V? Well, if I put the source charge at the origin, this just becomes 1 over r. The distance away from the origin. Like we did earlier today, when we put it at the origin, RSO just becomes r, the polar vector, polar coordinate. Okay? So if I hold what will a level curve look like for this? Circle. Yeah. So the level curves are concentric circles. Now, when you get farther away, the potential gets smaller, and kind of you keep track of it, they get spaced out. So when they're really bunched up, close together, here, right, they get really close together, and when you get farther away, they spread out. But they're always circles. Okay.
So where the 4 pi comes
It's 4 pi because it was a point charge, and so it really goes back to Gauss's law. Ultimately, if it has spherical symmetry, you expect 4 pi's. If it has cylindrical, you expect 2 pi's somewhere in there. Yeah.
Just kind of roll with the further away you get, the bigger the potential energy because the things are further apart or something. Forgot how you said it.
You're really close to not energy. All right, but okay. What I want you to do,
voltage, it's electrical potential energy. Is that what a volt is?
a volt is the potential energy per charge. So it's not energy. So like, I have to know how, so the voltage tells me if I move charges across, it tells me how much energy per charge. So if I do like 2 electrons, I get twice as much energy. If I do 4 electrons, I get 4 times as much energy. If I did, right? So to get the energy, I should take the voltage multiplied by the charge. So V is the energy per charge. And you have to do some extra multiplication. Yeah, it's kind of like, it's the would-be energy you'd get out per charge.
Yeah, there's an energy, but it's not.
Per charge, I said. So it's always, yeah. All right, what I want you to do is to just sketch, for small town, not much to do. So just while we're at it, we've got this thing here, got some function, got some level curves. And given the way I started class today, for no particular reason, let's just kind of sketch out what you think the gradient of V might look like. Or maybe even minus the gradient of V.
Gradient of V or the gradient of BS?
Well, VS, but which way do level curves point? The gradient's going to point in the direction of steepest slope, right?
Yeah.
So these are the level curves. The slope is going to go which way? Which way should I walk to go uphill? Towards the center, right? So the slope, so the steepest descent lines are perpendicular to these lines of, right? And I go uphill, or I go steepest going uphill, so minus that would be downhill, yeah. So these lines are like that. Oh,
So it's like the electric field.
whoa. Whoa, yeah. You get the idea. Holy crap. So if I were to just like draw lines following the curves of steepest descent, I would get lines which look like this, and I would go up, and it would be symmetric, right? It looked kind of like, electric field lines. Huh. Well, wait a minute. Going back to that rectangle of pain and suffering, in fact, this is just the electric field. That is what it is. So, how much, if you have a point charge, how much electric field do you get that goes around the point charge? None, right? It's all radial. And from this language, you say it's because the gradient only points radially. It doesn't go along the circles, it goes perpendicular to circles. So, okay. So that means that if you had some sort of shape, if I said that there was some set of contours for the equal potentials, maybe I said, everywhere here was 3 volts. And I said, everywhere here was 2 volts. And I said, everywhere here was 1 volt. Right? Just imagine some shape. Then you can kind of sketch what the field lines have to be. Because whenever a field line crosses an equal potential, what angle does it cross with? 90 degrees. So I could just say, I don't know, it's got to cross at 90 degrees, it's got to cross at 90 degrees. So there must be a field line like this. And okay, so here it's got to be at 90 degrees and 90 degrees, and it's kind of tipped a little bit, so it's there. There you go. Okay, so you can, if you know the level curves of the electric potential, you can reconstruct what the field lines look like. But remember, if you know the field lines, then in principle you can reconstruct E. So if you know V, you can reconstruct E, and vice versa. Okay. Now, talk about minus signs. If Q is positive, then when you get close to it, what happens to the potential? Does it go up or down? If this is positive, if you make R small, is this thing getting bigger or smaller? Bigger. Big is positive, it's getting bigger. If Q is negative and you get close to it, this thing's getting more negative, more and more negative. Okay? So when you walk near a positive charge, the potential goes up, V goes up. When you walk near a negative charge, V goes down. Think about a battery. The negative side of a battery has too many electrons. So when you walk near it, your potential is going down. It's the negative side for voltage. The positive side on a battery has missing electrons, so it has a net positive charge. So when you walk towards it, it's like your voltage is going up. Why am I saying this? The hardest thing about these problems is the minus signs. So the way to remember it, the way I remember it, is I imagine, basically I can always figure out up to a minus sign the answer, and then I think, oh crap, am I gaining or losing? I say, well, am I walking towards a positive? Then it better go up. If I'm walking towards a negative, it better go down. And that's how I get my minus signs fixed. Okay. So, one last thing. If you had no electric field in a certain direction, in some direction. So that would mean in that direction, how much change do you get in the potential? 0. Okay? You guys all knew that. Why are you guys looking at me like you never heard that? Haven't you heard that? Tim Piazza told you that. Tim told you exactly that. Right? You have a wire. What's a wire made out of? A metal. What's the electric field inside a metal? 0. Huh. So that means the electric field 0, so that means that the potential here is the same as the potential here, is the same as the potential here. The electric field is 0, therefore the potential is constant along the metal. What's the potential drop on a wire? What's the, if it's constant, what's the drop? None. Okay, so you have seen it in different.
You see,
I didn't expect you guys
the
to.
way a physicist might say something, and the way an engineer might say something are a little bit.
Yeah. One of the goals of this, though, is for me to unwind all the little rules of thumb that Tim teaches you. Where did they come from? Why? This is why. And you can immediately see, oh, all those things that we said in circuitry, they actually underlying them are all these assumptions or statements that need to be said about forces and electric fields and things like that. So, anytime you have a piece of metal, there's no electric field. That means that when you walk around a piece of metal, the potential can change. So the potential must be constant. It doesn't have to be 0, but it is constant. So like if I had a battery problem, whatever, and then I have a resistor, whatever, okay? We haven't talked about resistors yet. We haven't really talked about batteries yet. I'm just using the fact you guys all know they exist. But what do I know about the potential along this wire? Does it change? Does it change here? No. Now, they're not necessarily 0, but I know they don't change. There's one constant here, one constant here. If one is 0, then I say, oh, I've grounded it. Now I declare that one to be 0. That's really a choice. What I'm really saying is I'm just going to measure everything else relative to this point. That's fixing that constant so that I just make it so. Okay, let's stop there. Next class, we'll pick this up. And I'll remember my notes.